Welcome everyone to 11.11. This is additional applications and problems for the Taylor polynomials. Now this is not exactly how it is in the book, but this is actually more related to how our web work homework is going to be. So there's a lot of things you can do with Taylor polynomials. So these are some of them. These are some more of them, I guess, that we're going to be expecting you to do on homework, maybe quizzes, exams, things like that. So first of all, we're going to use Taylor polynomials to calculate out terms of various binomial series. We'll multiply known Taylor polynomials to find terms of Taylor polynomials for additional functions, things that we haven't thought about yet. We'll use Taylor polynomials to help evaluate limits, Taylor polynomials to determine what a series converges to. That's an interesting one because so far we've only dealt with does it converge or not. We never really asked, well, okay, it converges, what does it converge to? Because that's a difficult problem. And then finally, we're going to state and apply Taylor inequality, and that's going to be a better way to find remainders. Okay, so let's get to it with the definition. So first I want to tell you about this generalized binomial coefficient. So generalized because normally binomial coefficients only deal with integers, but here alpha in this case can be any rational number. That's going to be the case that we're dealing with. So alpha choose 0 is always equal to 1. Alpha choose 1 is always equal to alpha. Alpha choose 2 is 1/2 alpha times alpha minus 1. And in general, if you want to do alpha choose n, this is alpha times alpha minus 1 times alpha minus 2 times, and you keep on going to just 1 before the number you're choosing. So n, well, 1 before that would be negative n plus 1. And then you divide by n factorial. So this is the generalized binomial coefficient. So let's go ahead and use this to find some binomial series. Or this is really Maclaurin series, right? So we're using this property up here back in 11.10.7, right? That says 1 plus x raised to the kth power is equal to some sum of this k choose n times x to the n, summing from n equals 0 to infinity. Okay, so here we are. We have 1 plus x cubed raised to the negative 1/2. So, and we know how to write 1 plus x raised to the kth power, right? So in this case, we can already see that our k is equal to negative 1/2. So we're going to be applying this for a very specific case. But now we don't just have x, we have x cubed, right? So I'm going to switch these over. I'm going to make these u's, right? And the idea is that u needs to be equal to x cubed. Okay. So therefore, if I wanted to sum, therefore if I wanted the binomial series for 1 plus x cubed to the kth, that's going to be the sum from n equals 0 to infinity of k choose n of x cubed to the nth. So of course we can simplify this down and just make it x to the 3n. Okay, now let's go ahead and deal with, we have a very specific k, right? Like I mentioned before, our k is negative 1/2. So let's go ahead and input that in there. 1 plus x cubed raised to the negative 1/2, summing from n equals 0 to infinity of negative 1/2 choose n times x to the 3n. And we just want the first 4 terms. So let's go ahead and write this out. We'll do n equals 0 through n equals 3, I suppose, right? 0, 1, 2, 3, that's going to be 4 terms. Perfect. So negative 1/2 choose 0, x to the 0, plus negative 1/2 choose 1, x cubed, right? So when I plug in 1 for n, I still get x cubed. Negative 1/2 choose 2 times x to the 6th, plus negative 1/2 choose 3, x to the 9th. And of course, this would go on forever, but we just want the first 4 terms. What are those? So now we need to know how to evaluate these general binomial coefficients. So negative 1/2 choose 0. Well, alpha choose 0. Any alpha is just 1. And x to the 0 is also 1. So that one's just 1. All right, when I do alpha choose 1, that's just equal to alpha. So that's going to be negative 1/2 x cubed. And now negative 1/2 choose 2, right? So there's going to be a couple of them here. So I'm going to have negative 1/2, and then negative 1/2 minus 1, so that's going to be negative 3/2. And then you divide that by 2 factorial, or 2 if you'd like. and that's times x to the 6th. And then alpha choose 3, that's going to be negative 1/2, negative 3/2, and then negative 5/2, right? So we stop 1 before 3. So we go, there's 3 terms altogether, but we go to alpha minus 2, right? And 1/2 minus 2 is our negative 5/2. So that's where we stop. And then, of course, we divide this all by 3 factorial. And then we have an x to the 9th plus dot, dot, dot. All right, and then let's do one more line to simplify this down, be our final answer. So 1 minus 1/2 x cubed. And now if we simplify this, it's going to be, what, plus 3/8 is what I'm getting, x to the 6th. And then let's see, there's 3 negatives, so that's going to be minus, let's see, the 3 and the 3 cancel here. Looks like there's 4 2's in the denominator, so that's going to be 16, a minus, and a 5. So negative 5/16 x to the 9th. And then the next one would be plus, and it would keep on going forever and ever and ever. But those are the first 4 terms of the binomial series. If you want to have some fun, of course, you can graph this along with the original function, and you can see, hey, these things look pretty close, at least around 0, right? Because this is a Maclaurin series, so it should be close around 0. Okay, find a Maclaurin series for the function cube root of 1 plus x and find its radius of convergence. So this one we need to identify, hey, cube root is the same thing as raised to the 1/3 power. So this is really a binomial series expansion, just kind of in disguise. So we know that according to our theorem, that if you want 1 plus x raised to any old k, this is going to be a sum from n equals 0 to infinity of k choose n. Well, in our case, our k is 1/3 times x to the n. This is, of course, by our theorem 11.10.7, way up here. There it is. And notice right there it says r equals 1. This is telling me my radius of convergence, and it doesn't matter what k is. All the k's out there, the radius of convergence is always 1. Oops, went past it. Too excited. So by 11.10.7, we know that the radius of convergence is 1. Of course, we could also figure this out by using a ratio test, but that's going to be a little bit complicated with these binomial coefficients, so I'm glad to not do it. All right, find the first 3 terms of the Maclaurin series of the function e to the 2x times sine x. So I told you at the beginning that we were going to be able to multiply together known Taylor-Maclaurin series and get more complicated Taylor-Maclaurin series for new functions, right? So we know e to the 2x, and we know sine x, what the Maclaurin series are for these things. So let's go ahead and start writing them down. And then the idea is that if we start foiling these all out or expanding these all out, we'll be able to get the Maclaurin series for e to the 2x times sine x if we do this carefully, at least the first 3 terms. So e to the 2x, well, we know what the series expansion is for e to the x, so let's just plug in 2x everywhere we see an x. And then for sine x, we know it's alternating back and forth, and we only care about the odd powers. So x to the 2n plus 1 over 2n plus 1 factorial. So let's go ahead and start writing out a few terms of these. Again, we don't need to write out all of them because we only care about the first 3 terms for this multiplied together thing, this e to the 2x times sine x. So if we start writing out a few of these, we have 1 plus 2x over 1 factorial plus 2x squared, which is the same thing as 4x squared, right, when you distribute the squared. Divided by 2 factorial, and this would go on for a while, but since we only need the first 3 terms, I probably don't need more than 3 terms here. And then for sine x, if I plugged in n equals 0, I would have x divided by 1 factorial. All right, it'd be positive there. And then we'd have minus x cubed over 3 factorial. And again, this is back in theorem 11.10.7, but we need to get good at plugging in different values for n. And again, I'll stop after 3 terms. That's probably all I need. And so f of x is supposed to be these 2 things multiplied together. So let me go ahead, I'll copy this down, 1 plus 2x plus 2x squared times x minus x cubed over 6 plus x to the fifth over 120, which is the same thing as 5 factorial, and it keeps on going. So now let's try to FOIL this a little bit, or expand it really. So I want to figure out, okay, what are all the ways that I can multiply by things in order to get constants, right? Well, in order to get a constant, I would need to multiply a constant by a constant. But there's no other constant in this sine x expansion. So in this case, it's going to be 0. How about ways to multiply this stuff together in order to get a linear term, right? X to the first power. Well, I could do 1 times x. That would be great. That would give me 1x. And is there any other combination that would just give me x to the first power? And the answer is no. There's really no other way that we can multiply these things together, right? Because all of the terms that I'm forgetting about have higher and higher powers of x. So those aren't going to help me. How about x squared? Is there any way I can get x squared? Well, there's 2x times x, so that'll give me 2x squared. How about any other way? No, unfortunately not. There's no other way to get any squared terms. Okay, but now the claim is that it gets a little bit more interesting. I know I only asked for the first 3 terms, but I'm going to do a 4th term for you just so you can see how this can become more complicated. So I'm going to try to find cubes, right? Different ways I can multiply things to get cubes. Okay, so first of all, I could do 1 times negative x cubed over 6. So that's going to be negative 1/6 x cubed. So that's one way I could make cubes. And I could also do, let's see, I have this 2x squared times x. So if I multiply these together, I could get, 2x cubed. And now everything after that's going to be too big, right? So this is actually the first 4 terms right here. And then you could talk about, okay, different ways to make x to the 4th, different ways to make x to the 5th. 0 plus x plus 2x squared plus 11x cubed. I simplify that down. Many of your web work homeworks will actually ask for like the first 3 non-zero terms. So this would be a good answer there. These are the first 3 non-zero terms. It's actually the first 4 terms if you include the 0 at the front. All right, so that's how we can multiply these things together. We can actually also divide, which is a little bit more complicated, but we can certainly do it. So if you wanted a Maclaurin series for f of x is x divided by cosine of x, well, let's see how we could find that. First of all, cosine of x, we know the Maclaurin series expansion for this. We only have even powers and they alternate. All right, so it's going to be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, so on and so forth, back and forth forever and ever. And we know whatever our f of x is, if I multiplied it by cosine, I have to get out the polynomial x, which is pretty remarkable. So whatever f of x is, I'm going to use my c sub 0, c sub 1, c sub 2, right? These are all the coefficients in front of x, x squared, so on and so forth. If I were to multiply cosine times f, I should get out x, right? Essentially, this is just multiplying through by the LCD. And this is pretty remarkable, right? So on the right-hand side, many of the terms are 0. The only one that's not 0 is the x term, and there's just a 1 out in front of it. So if I was to take my f, here it is. Again, I want the first 4 terms here. So 0, 1, 2, 3. And if I was to multiply by cosine, I should get out just x. Now 6 factorial, this is the same thing as 720. Okay, so equal to x. Well, another way you can write x is 0 plus 1x plus 0x squared plus 0x cubed plus ... And again, so we're going to multiply by these things together to figure out all the different ways that we can make constant terms. So like c0 times 1. We're going to try to figure out all the different ways to make linear terms, all the different ways to make quadratic terms, all these sorts of things. So I was to take c0 times this x squared over 2. I get my negative c sub 0 over 2 times x squared. Now let's maybe take c0 and multiply it by 1 more here, this x to the 4th term. So I'd have C0 times x to the fourth over 24. And that's probably enough. I mean, I'd have an x to the 6, I'd have x to the 8, so on and so forth. Probably don't need those. Let's move on to the next one. C1x, and I'll multiply it by 1 first. So C1x, that's it. Then I'll multiply it by the x squared over 2 term. So that's going to be C1x cubed over 2. Then I'll multiply it by the x to the fourth over 24 term. So that's going to be C1x to the fifth over 24. That's probably enough. X to the fifth is probably too high. I probably don't need that as is, but it's fine to write down too many terms. Now let's start multiplying together our C sub 2 times x squared. First by 1. There we are. Now by x squared over 2. So this is going to give me my negative c sub 2 x to the fourth over 2. And that's probably a fine place to stop, but I'll do one more just in case. I'll get an x to the sixth term here. C sub 2 x to the sixth over 24. And let's do one more of these, my c sub 3 x cubed. So if I was to multiply that by 1, there we are. And let's also multiply it by our negative x squared over 2. So it's going to give me negative c sub 3 x to the fifth over 2. Okay. And the idea, again, is that this needs to be equal to just x, which is the 0 plus 1x plus 0x squared plus 0x cubed. So let's get together all of the constant terms. Well, there they are, right? C sub 0 has to equal 0. That's the only way this is going to work out. Okay, how about all the linear terms, all the things with just x to the first power? Well, there's only one of them, right? C sub 1 times x. Well, this tells me that c sub 1 has to be 1. Okay, what about all the squared terms? So here's a squared term. Looks like I have another one here, and that's it. So this is now a little bit more complicated, right? It's telling me that C1 minus C sub 0 over 2 must equal 0. Oops, sorry, not C1, C2. There we go. Let's go ahead and correct that. Again, we already know C sub 0 is 0. So therefore, C sub 2 has to also be 0, solving this equation. One more, C sub 3, I think this one's interesting. So let's put together all of the cube terms. Yes, I guess we'll go ahead and use purple here. So here's a cube term, here's one, and I have one more, way over here. So this is telling me that negative C sub 1 over 2 plus C sub 3 needs to equal 0. Right? Because the left-hand side needs to equal the right-hand side. Now, C sub 1 we already know is 1. So let's go ahead and add 1/2 to both sides. And we get C sub 3 needs to be equal to positive 1/2. So therefore, we now know the first 4 terms for our Maclaurin series, right? We know that C sub 0 has to be 0, C sub 1 has to be 1, C sub 2 has to be 0, C sub 3 has to be 1/2. So we can plug those into our F formula. And there we are. Those are the first 4 terms. And we now know how to multiply and divide. All right, and that's going to be a good place for us to end this video. You can see there are a lot of things you can do with Taylor series, including, multiply 2 known Taylor series together to get another one, and also doing a little bit of division, which is complicated but doable. All right, so why don't we take a quick break, and when we come back, more examples. See you shortly.